watch an educational streamer or whatnot, you can. But before we jump into any of the boring testing mumbo jumbo, let's play a little game with math. This is Brainzilla, the site. It's a really fun site I like to use sometimes. What they do is they have a bunch of little things that they update daily, like for instance, these logic equations, as they're called, updated at midnight, at 12, at 4 p.m., and 8 p.m. Right. Oop. And everything is going accordingly, I hope. Sorry, I'm just trying to make sure that everything is working well, but I'm not sure if it is. So give me 1 second. Okay, yeah, everything is. And yeah, you can see it. So without further ado, let's start. And I have played this on stream before, but if you don't know what this is, that's perfectly fine. And I'll explain it. What this game is basically A, B, C, and D are 1, 2, 3, and 4 respectively. One of them is 1, one of them is 2, one of them is 3, one of them is 4. For each a letter corresponds to a unique number, and always each number corresponds with the unique letter. And we use these equations on the sides to solve for them. And some other useful things to know is that the numbers are always integers, and that the numbers cannot be below 1, and cannot be above 4 for the 4 by 4. 5 by 5, it's 1 by 5, 1 by 5. There's 5 different letters to solve. But yeah, so without further ado, let's get started. So the first thing we note is 2c is equal to d, which implies c is at maximum 2, because 2 times, well, 2 is 4, in which case c is 4, and the d's possible maximum in the entire game in this little mode of 4 by 4 can be 4. So c cannot be 3 because that would imply that d is 6 and d is not 6. However, we can also conclude that d is even, either 2 or 4, because it's twice c. So, little known fact for the even numbers, which is very common sense, but it's also proven and blah, 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 is that an even number is just 2 times any number. Like, that's how they do it in proofs. An even number is always just 2 times any number. So yeah, so this just is literally the proof for an even number. So d is in fact an even number. Furthermore, we can double prove this by just saying 1 times 2 is 2, and 2 times 2 is 4, and those are the options for d, only possible options for d. Right, and we know between c and d, one of them has to be 2 as well, just from the nature of this game, because if c is 1, d is 2. If c is 2, well then c is 2, and we already have that rooted out. So that's fine, and fun, and dandy. Now we have c plus d is equal to b, which eliminates 4 for d, because if d was 4, then c, which is a number that's greater than 0, added to it would make b, greater than 4, which is impossible. So d is 2, c is 1, and then b must be 3, which leaves a at 4. And that's a little fun, a little nice, little dandy. And you'll see this Greek logic, Kyudoku, and logic puzzles. We might do a little bit of those later before jumping right into the SAT, just because they're fun. Oh wait, I forgot to pull up Stream Manager. I'm such a klutz today. All right, yes, I do apologize. I am streaming on one screen, so it is a bit hard for me sometimes. But yeah, I can pull it up, and yeah. So yeah, that's good. Right, now we're on the 5v5. So first thing we note is, we'll notice the first one, a plus d is equal to e. Now we know a and d cannot be 5, just because if they were 5, then e would have to be greater than 5, which is impossible, considering a plus something would be equal to e. But if a was 5, 5 plus something is greater than 5, which e cannot be. Same thing with d, same logic. Behind it, d plus 5 plus a, or which is something, cannot be is greater than 5, which is impossible. Furthermore, for e, we can say e is not 1 or 2, because the lowest sum of integers we have is 1 and 2. Like, let's say a is 1, d is 2. The lowest possible sum of that is 3, so that's what we know. Furthermore, we can apply this logic to c plus d is equal to b. So we know c can't be 5, and we know d can't be 5. And considering we could do the same thing we did with d, where basically, what was it? Oh yeah. Oh wait, why did I do that with d? That's my apologies. I misread it as c plus e is equal to b, which is incorrect. So yeah, c plus d is equal to b. So c plus d is equal to b. So we can do the same thing that we did before. where, considering C, we eliminated the last term for C, eliminated the last term for D, neither thing can be 5. But for B, again, the minimum sum is 1 plus 2. And we don't know, one of these numbers can be 3. That's all we know. We don't know if it's higher, we don't know if it's lower. We know one of them can be. So we can't really use that to eliminate the other one. For instance, we can't use that B is 3 because we don't have it to eliminate E as 3. That's incorrect statement. Right. So now we're really relying on the last equation. B plus D is less than or equal to 5. So B plus D is less than or equal to 5. Here, I will substitute in B in this equation because we have C plus D is equal to B. So we will rethink this as C plus 2D is less than or equal to 5. Now we know D can't be 4 or 3 because let's say, let's eliminate the C from the equation that we just made. So that only 2D is less than or equal to 5. We're just eliminating it, which isn't even correct. Let's just do that. If we do that, then we know that, 2D is less than 5, which means D at most can be 2 because 2D would be 4, which is less than or equal to 5. If D was 3, that would be 6, which is greater than 5, and not less than or equal to. Furthermore, we can conclude one more thing. Again, C plus 2D is less than or equal to 5. We know between C and D, one of them has to be 1. Because if D is 2, C must be 1, because that's the only possible combination of numbers that work. And otherwise, let's say D is 1, well, D is 1, so we don't have to worry about that. So we can cross off A as 1, as I just did. And let's see. Right. And unfortunately, that's not bringing us a lot, but it does bring us a good amount of something, good amount to think about. Right. So now we're going to have to use our brain and think just a little bit. We might have to do some plugging and chugging just to whittle it down. But yeah, we have A plus D is equal to E, and C plus D is equal to B. Here we can subtract these two equations from each other and move them around to be A plus B is equal to C plus E. A plus B. So the sum of A and B is the same as the sum of C and E. So A and B, the sum of that is equal to the sum of C and E. And we know that it's probably going to, both sums are probably going to be equal to 8, I would assume, just off guessing. Because, or not 8, wait, did I mean 8? I'm actually not sure. Well, Okay, that was a bit foolish of me. However, A plus B is equal to C plus, E. So possible combinations are A and B being 1 and 3, C and E being 1 and 4, but that's impossible because then nothing's 5. So we have to remember that either E or B has to be equal to 5. However, we know, that was foolish of me. I didn't eliminate B as 5 earlier from the bottom equation. Because if B is 5, B plus something, 5 plus something is greater than 5, which is not less than or equal to. So E must be 5. I do apologize, I should have realized that sooner. However, if E is 5, that's A plus D. So either A and D are like this, 3 and 2, or 1 and 4 between A and E. However, if, and that does actually work if we do C and B there, which I wasn't expecting to work like that. But yeah, also I will say these only have one solution. So if you think you're going in one direction that you think is right and nothing's wrong yet, you probably should go in that direction because you're probably not wrong if things are fitting in. Maybe. It's a bit tough. So the first thing to note, 4A is equal to E, which means it has to mean A is 1 and E is 4 because there's no other multiple of 4 on this, board. Further, we see 4A is equal to 2B, or 2A is equal to B, and we already have A, so we know B is 2. Then 2C is equal to D. Well, 2C has to be the only non-odd thing, and 2C is 3. Let's suppose C is 3, the minimum number. That would mean D is 6. D cannot be higher than 6, so D must be 6, C must be 3, and that leaves us with 5 for F. This one was fairly easy. Now we're moving on to the 7 by 7, right? And off the bat, we noticed E plus F is equal to 2A, or E plus F is even, so either E and F are both even or E and F are both odd. Further, let's go with 2A is equal to CG. One thing to note is that we can equate these two top equations, so I'll eliminate everything, though that's not going to be of use yet. So we know E and F are even and C and G are even. However, we also know that C and D are even and B and C are even. And let's count up the numbers we know, sorry, not even, that add up to be even. C and G add up to be even, that's 2 numbers, but then C and D also add up to be even, and which implies 3 numbers, because if C and G add up to be even, they're either both even or both odd. If C and D add up to be even, they're either both even or both odd. Considering C and C on these two equations have to be the same, we can conclude that if we subtract them from both equations, or sorry, not if we subtract them, we can conclude that G and D are either both even or both odd, because when added with C, they both turn out to be even. So they both complement C in that sort of manner. Furthermore, we can say the same thing about B. So we have G, C, B, and D all together. They're either all even or all odd. However, one thing to note about this board, it's a 7 by 7. There are only 3 even numbers, 2, 4, and 6. So for them to be the same thing, either all even or all odd, they kind of have to be odd. So we can eliminate all the even numbers from C, G, D, and B. So all the even numbers from C, G, B, and E. So I'll just do that quickly. And a second thing to note is because all the 4 odd numbers are taken up between B, C, E, and F, we can eliminate all the odd numbers for the D, A, and G. So we'll do that right now. And again, we can do that because they're all taken up. Even though we don't know which number is which, we do know that they're all going to be taken up. So these values are limited. And further, we can, I guess, prove this more by E plus F. Oh, wait, did I do E plus? No, C, G, D, and B. C. Oh, I did this wrong. That's my bad. C, G, B, and G. I do apologize. I messed up writing that. That's why I was confused. But yeah, same logic applies. So we'll cross out everything that's, well, impossible. And yeah, we're in a good place right now, and that's really nice. One thing to note, again, the 2a E is equal to E plus F, and the 2a is equal to C plus G. We will use that in just a bit. Here, I want to make sure everything's working correctly, and it does seem to. So I'll hop back right to the game, and I will think. Right. So first of all, let's use the equation we haven't used yet. E is greater than C. So E is greater than C. All right, so C cannot be 7. That's the only thing we can conclude from that for now. I'm going to cross it out for now, but yeah. And I do like these equations. They're actually pretty fun because they're more difficult than what they are commonly. Like, here, let's hop over to H for a second. You see this? This is actually a bunch of simple equations that we can run over. Like, for instance, we already know that C is greater than H, B, and G. In fact, it's 6 greater than G, so C is either, 7 or 8. However, we also know that H is the greatest of these 3. H is 1 more than B, and B is 2 more than G. And that's just a guessing. Furthermore, we know H is equal to D plus 4. Or in other words, C is equal to D plus 7. So we already, like on this one, we know C is here, and D is the minimum. Just because of this equation up here, and that equation down here. Because we can substitute for H, and we get C is equal to D plus 7. And the only number that you can add 7 to is 1, because then you'll get 8. But yeah, that's a little bit jumping ahead. But that's what I wanted to bring up. I just wanted to bring up that I do appreciate those things. Right. So now I think it might be best to go to the 2a. So we know a is an even number already. And let me get some water. Furthermore, because A, E, and F, they're all even, we know A is the midpoint. Because A is, based on this, we can rewrite this formula as A is equal to 1/2 parentheses E plus F. Or in other words, A is the average of E and F. So we know what E and F have to be, I suppose. E is 6 and F is 2, or vice versa. So that's good. We kind of determined A from that, which I wasn't even expecting to do, but it worked out properly. Normally, it's in the odd column A, I would suppose, in other examples. However, what I wanted to showcase was that 2a is equal to c plus g. Also, we can also note, I suppose, that 2g is equal to c plus d, and maybe try to substitute that in, but we don't really need to now. We know that 2a is equal to c plus g. So let's look at all the possibilities for c and g that are equal to 2a. So we know c can't be 7. So one combination is c is 1 and g is 7. Actually, no, let's do the first thing. We can eliminate g is equal to 1, because if g is equal to 1, c must be equal to 7 to come out to 2a, which would be 8, or 2 times 4. So we can eliminate that. We know c and g can be 3 and 5, 5 and 3, whichever matters, but they can also be, c can be 1 and g can be 7. And we don't know yet, so we'll just keep it like that. Here, I just want to see, e is greater than c. That's what this says here. This technically isn't math, this is more so logic. However, if e is greater than c, that, considering, and this is kind of more of a guess, it could, technically, it doesn't necessarily mean you can write. However, let's assume that e is 6. Let's assume that. This technically isn't a good thing to do. In fact, it can be wrong. C can be 1, in which case e would be 2. However, yeah, we're going to assume that because it makes everything easier. And we'll assume that f is equal to 2. We can't prove it. However, it is likely that it is true like that. Again, we could be proven wrong, in which case we're going to have to undo that. This is an assumption, not a statement, so I would like to make that clear. Right. So let's start with 2f is equal to b plus c. 2f is equal to b plus c. Oh, wait, what? 2 times f, 4 is equal to b plus c, which case c and b are 1 and 3 respectively, technically speaking. And I guess this is throwing a wrench to our plans, a small wrench. Actually, no, this actually proves that we're right. And I'll show you why, actually. Let's assume f is 6 and e is 2. In that case, c would have to be 1. But let's look at this equation. 2f, or 2 times 6, or 12, would equal to b plus c. But c is 1, so b must be 11. That's impossible. So that just proved our point, that e is in fact 6 and f is in fact 2. That is 100% proof. Right. Next, let's look at some other things. So we can basically eliminate the e is greater than c, because regardless of what value c we put, either 5, 3, or 1, we know that e is always going to be greater than that, considering e is 6. Right. Next, I suppose we should hop on the, let's do, considering a and g are both, or no, we know, okay, we already limited the values to c and g, so whatever. We'll move on to 2f is equal to b plus c, the bottom equation. And we're using that because we don't have any, for the middle equation, we don't have anything. We don't have g, we don't have c or d. So, but for the bottom equation, we do have f. F is 2. So b and c are either 1 and 3. So we can eliminate 1 and 3 from literally everything else. And we can eliminate 5 and 7, and that's perfect. So now we're down to, well, 2. And we can eliminate this equation from use because regardless of the values put in it that are left, it's always going to be true. Right. 2a is equal to c plus g. That's our first thing. So 8, or 2 times 4, is equal to c plus g. C, and where's g? All right, we don't have much off of that yet, considering there's 2 possible situations in which cases this works. However, we can use 2g, or first off, let's note, 2g is equal to c plus c, g must be 5. Why? Because if g was 7, that would mean 2g or 14 is equal to c plus d. C and d must both be 7, which is impossible. In that case, d is 7, and then c would have to be 3, in which case b is 1. And that is our answer. Right. Let's move on to 8. And 8, I do apologize, we did this a bit already. but we use these two equations so far. C is equal to h plus 3 and h is equal to d plus 4. We substitute them in, and we got C is equal to d plus 7. And the only number, when you add 7 to it, 1 is the only number, in which case you can add 7 to it and get 8. Because 1 is the minimum, 8 is the maximum. So we know that. And we can eliminate, well, we don't really need to eliminate them yet. We know let's start with C is equal to G plus 6. That means G must be 2. C is equal to B plus 4. That must mean B is equal to, well, 4. And H plus 3, that means H is equal to 5. And the last equation, A is equal to F plus 3. A is equal to F plus 3. There's no value for F, so we know A is 6 and F is 3 because those are the only two values that work, which is E is 7. Yeah, and you'll notice that sometimes difficulty just varies like that. You know, we spend a lot of time on 7, but not so much on 8. And it's fine. And now we're on 9. And these are the equations I like the most. The A plus E plus H is equal to 22. The 3 variable, but 1 equal to 1 constant. However, what I don't like, because it makes it a little bit too easy, is this. We have A plus E plus H is 22. However, A plus E is equal to 15. So let's substitute that bottom part into the top equation. H plus 15 is 22, or H is 7. I don't like that because that was just a bit too easy. But yeah, now we no longer need the first equation up top, and we can unclick everything else. And let's see if there's anything else that drastically catches our eye that the first two equations have done. Oh, I have one here. Let's eliminate these two. D plus H is equal to 8. Well, we already have H, so and D must be 1, just because those 7 plus 1 is equal to 8. Right. So let's unclick these two equations and continue. We have C plus I is equal to 7. So that means C must be less than 7 and I must be less than 7. So we can eliminate 8 and 9 and 8 and 9. Considering 7 was already eliminated, we can eliminate all the higher values. And we also can eliminate 6 for both of them, because the only value that works, C plus I is equal to 6, is one of them has to be 1. However, D is already 1, which makes it impossible. So it's either 2 and 5 or 4 and 3, which is good. We eliminate that rather quickly. Right, now we're on to F plus H is equal to 11. We already have H is 7, so F must be 4. In which F plus H is, oh, I accidentally clicked 3. 4, in which case C must be equal to 3. 4, wait, did I do that wrong? Oh, I did. I accidentally clicked F on accident. That's my bad. When I was meant to click C plus I. But we still do know that F is 4. Right. And where's F? It's right here, and F is 4. Perfect. Further, because of that, we can eliminate 3 for C and I, because the only combination that works is 3 and 4, but 4 is already used. So we can eliminate, C plus I must be 2 and 5 respectively, so we can eliminate all 2 and 5s from everything else. That's not C and I. Right? Yes. Okay, we did everything correctly. So now we are B plus F plus I is equal to 9. So we don't have B, we do have F, and we don't have I is equal to 9. Well, we know I can't be 5, because if I was 5, I plus F, or 5 plus 4 is 9, and then B would make that impossible. That would make it greater than 9. So I is 2, which means C is 5. So I plus F, 2 plus 4 is 6, and then B must be 3, and that solves that equation. A plus E is equal to 15. Do we have E? Do we have A? No, but we do know that they have to be 6 and 9, because those are the only two numbers left, and we know G must be 8 in the final. And we know E plus G is equal to 17, E must be 9, and then that leaves A as 6. And I did go a little fast there. I do apologize. However, I think it's a little bit, sorry. I think I shouldn't, because it's a bit redundant, I feel I shouldn't have stressed it as much. So I do apologize if I went a bit faster. That's unusual for me. But here, let's go on to Kidoku. We're just going to play a few games. Kidoku is fun. It's sort of like a Sudoku, but instead there's it's a 6x6 box, and in the box you must circle the numbers 1 through 9, 1, 2, 3, whatever, all the way to 9. One of each, and each column they add to at most. So for instance, let's say this was 9, it's impossible because there's already 3 circled, right? And considering there's one of each number, we can eliminate all 3s on the board. Right there, and this one, right. And we can make a sign consistent in this row of 3. We can eliminate this 9, and yeah. This is very easy because, not because of what we eliminated so far, but because of, well, everything else, I suppose. So let's do it. There's a 9 here, there's a 9 here. I know the can't be there. However, there's no other on this board that I see, so we can eliminate both these 4s. In this row, there's 9, so 9 plus something is impossible, so we can eliminate the something. Now let's move on to 8s. There's a bit of 8s, so we can't really do anything with them. So, yeah, there's no cheeky trick that we can try, so we'll just not care about them. 7. There's 1. Yep, there's 1 7, so we can eliminate the 6, we can eliminate the 9, we can eliminate the 8, we can eliminate the 6 and the 5, with the 8, and yeah. However, we just eliminate one of the 9s, and now that's left is this 1 9, so we can eliminate this entire row, basically. Right? Yeah. All right. Perfect. So we got 9, 7, 8 are still a bit strong. There's 3 I see on my screen right now. Here, here, and here. So we can't really do anything with them yet. However, 6s, there's 2 of them, which is normally good. However, the 2 here perfectly fits both row and column, so I can't eliminate anything yet. And further, there's this 2 here as well. There's 2 2s, can't do anything with them either. Because the 6 plus 2, less than 9. 5 plus 2, less than 9. Speaking of 5s, we have 5 here, and 5 here. This 2 works though, and yeah, it's unfortunate. 4s, we got a 4 here, and that's the only one, so we can eliminate the 6. Which means this must be 6. Yep, both 5s, which means this must be 5, so we can eliminate both 8, which means this is the 8, and this has to be the 1. We can eliminate this 2 because 6 plus 3 is 9, and 2 can't fit in there. 2 is probably going to go here. Yeah, it has to. And I said it has to, but I should have said that 5 plus 4 is 9, and 2 plus that is greater than 9. Right. Now we'll move on to easy, and as we go on, it will get harder. So right off the bat, I'm going to eliminate all the 4s I see. I believe that's all of them, and I'll eliminate the row first. We can get rid of the 9 and the 8. We can get rid of the 7 and the 9. Perfect. Now I see 2 9s, but I don't see any other 9s on the board, so we can eliminate this entire column, not row. Apologies. Right. And now we can move on to the 8s. 8 here, 8 here, 8 anywhere else? No. So we can eliminate this row with the exception of the 1. 7, there's a lot. There's like some like around here, you know, and here, you know, and even here. 6s, 6 here, 6 here, and that's all the 6s. We can eliminate both 7s. 7s only on this row, so we can eliminate both 5s. 6, 5, 5 here, 5 here, 5 here, but this is a 2, so we can't really do anything. 4s, we have 4 circled. 3, 3 is probably here. I don't see anything else anywhere else. We can leave the 9, 7, keep the 6 and the 1, and we keep the 5s and the 2. 9 must be here because it's the only 9 left. We eliminate the 2 and the 8. 8 must be here, so we eliminate the 5. We have 2 5s, but this number is already blotted out, and this is a 2, so it does nothing. 7 7, whatever. 6 6, whatever. Actually not whatever. 5 4 3. There's only 1 2, I might add. So we can eliminate this 5 because this is 5 plus 5, it will be 10. So the 5, eliminate the 7, this is the 7, we can eliminate the 6, this is the 6, we can eliminate the 1 here because, again, 5 plus 4 is 9, 9 plus 1 is 10, which is greater than 9, and that's the 1. Right? I think it's lagging. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, and no rows or column add up. Right, here, maybe I'll throw in, yeah, I'll do the medium, and then, yeah, I'll do the medium, and that's going to be it for the numbers, and I might do some, what's it called? The Greek logic puzzles, or whatever it's called. All right, so let's start with 2. Let's eliminate the 7. I say the 8, not the 7. Yeah, that's going to be good, except for the bunch of 2s that we have, which are, only those limited 2s. Oh, and this 2. I see the 9 here, 9 here, 9 here, and 9 here. Can't do much. There might be more 9s, but I'm not even going to bother looking. Bunch of 8s, Yeah, can't really do much. There's also an 8 up here. But yeah, we can't do much with that. Now we're on to sevens. A ton of sevens on this row, here, 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 and here. Yeah, they're just everywhere. So we can't really do much with that either. So we're going to have to go to sixes. Sixes, six here, six here, six here. Is that all the sixes? I believe so. Yes, we can eliminate the 7 because regardless, it's going to be 6 plus 7, and that's 13, which is more than 9. Let's move on to 5. I hope we only have 1 5, and I think we do, which is actually pretty cool. It's the 7, the 6, the 8, and the 6. That's really nice. Oh wait, we can eliminate both 4s because 5 plus 2 is 7, and 7 plus 4 is 11, which is greater than 9. Oh, no, I can't do that. Because there's a 5 here. So we can eliminate the 6. We can't eliminate the 4 because it might not be this 5, which is unfortunate. Speaking of 4s, 4 here, and 4 here. Can't do much with that though. There's a ton of 3s, 1, 2, and a 1 here, a 1 here, and that's about it for 1, so we can eliminate the 9. And now we have 3 9s, and yeah, this one's actually really tough. I will give it that, because I didn't really eliminate much at all. Yeah, the 8s are still everywhere, the 7s are still everywhere, the 6s... Oh wait, I think might only be one... Nope, there's 2 6s. Right? To eliminate this 4 at the very least. And because of that, we know 4 must be in this row, so we can make the 7 and the 5, which implies this is the 5. We can get rid of the 8s, which means 8 is probably on this row. We make the 9, 7, and 7, which means the 9 is on this row. We make 7 and 3. All right, perfect. It was a bit slow, but we're getting the hang of it now, which is great, fantastic, lovely. We know the 1 has to be on this row. However, just for the sake of logic, I guess hear me out. The max sum of this row is 6 because it's 5 plus 1, regardless of which one it is. Max on this row is 1 plus 2 plus 3, or 6, because we can't have 2 3s. So I'm going to assume that this is the 1. I'm going to assume it's proper because it's the more likely to work. I can't disprove that this can't be the 1, but I can prove that this works as a 1 regardless of everything else. So I'm going to assume that. Right, so we have 9s, 8s, 7s. There's 1 7, so we can limit the 6, the 3, and the 3. 6 has to be here, limit the 8, 8 has to be there, limit the 9, 9 has to be there, limit the 4, 4 has to be there, eliminate the 3 because 5 and 4 is 9, and 9 plus 3 is greater than 9, and that's the 3. Perfect. I could go on and on, but that's a bit redundant. Right, here, let's do some Greek logic. We'll do the first 2 rows before, and this will be the end of our little math fun session. And yeah, these these games can be found for free at Brainzilla.com. I really love the site. I really, if they want to sponsor me, they can. I'm very open to it. But yeah, until that day, if that day ever comes, which it probably won't, we can just do our puzzles. We know the Omega has to go. Oh, sorry. I should explain these puzzles. So basically, same thing. There's like a grid 4x4, 5x5, all the way up to 8x8, which is insane. But on these grids, basically have these different symbols. You have, triangle dude, you have pitchfork dude, you have omega and theta. I just use pitchfork dude and triangle dude because I don't know what they're called, and I don't have to for this game. And for this game, basically, what you want to do is, again, there's one of these in each row. So for the omega, for example, it's like this. This is the 4. 1 in each row, 1 in each column, and 1 in each diagonal. Right? For each of these symbols. So for instance, let's say if I put the omega here. Impossible because this omega is in the same column as it. If I put the omega here, possible same row. Put the omega here, impossible same diagonal. And if I put the omega here, possible same column again. And we notice there has to be only, all right, so yeah, I think that barely explains it. I hope it explains it better than I hope you understand it better than I explained it. right? And this is a game that I feel you understand more as you play. Here, actually, there are rules up here. So actually, I'll read them in my narrator voice or something. I don't know, because I should have just done that originally. Drag and drop the Greek letters in the grid so that each letter appears exactly once in each row, column, and main diagonal. This game is updated 4 times a day, midnight, 12, 4 p.m., and 8 p.m. Right. So, and by the way, main diagonals, by that, what they mean is, you know, along here or along here. Diagonals from top right to bottom left or top left to bottom right. Either way. So again, let's start with omega because we know omega has to go, well, here. This spot occupied by the diagonal, this spot occupied by this column, and this spot occupied by this column, and the last one that has to go there for the column, row, and because there's nothing else on the diagonal, on that diagonal. Right, so that's the easiest one, I feel. Here, let's do the theta. Theta has to go here because this spot's occupied from the diagonal. However, and this spot is the only spot that's left. And remember, as you said before, each letter appears exactly once in each row, column, and main diagonal. So it has to appear once in this diagonal, and this spot's taken, so it must go there. Right. And next, I suppose, here. The bottom is fine. However, this diagonal, it has to go here for this diagonal, because if it went here, it would contradict with this row, which means the last spot is right there. And now we're on to Pitchfork. Pitchfork dude is there, which occupies this diagonal, which means it has to be here. And this is the last spot that's available. I'm sorry, and again, when I meant diagonal, I meant considering it's here, it occupies this diagonal, which implies that this is the last spot available. And then triangle dude, you know, we put him everywhere else because we haven't touched him once. And you might think the first one's easy, you might not. I forget what I thought of it after I first completed it. But this is something that goes exponentially harder as you get bigger. Like, I think I've only beaten very hard once, and I haven't tried it much because it's not fun. It's just a lot of trial and error and plugging in and really hoping. So it's not my style, I suppose, going so hard. But on the easy and even medium, they're fun, I suppose. And now we're on to this one, and I'll start with the theta because there's 3 of them. So we can eliminate everything on the right side and only focus on this side. And what I like to do sometimes is I just like to throw them on the board in all possible places they can go. Right, so they can all go there, and that's fine. However, one thing, like these are only possible, these are all the possible places for the theta symbol. Because on this top row up here, it's taken up by this one, and this bottom row is taken up by, well, this one back here. And yeah, and you'll notice sometimes there's a red box that'll appear around them. That means like they contradict the statement that we have. For instance, if I put one down here, look at even the solid box, the ones that are definitely there have a red box around them because this one down here violates the rule that we stated that it has to be one in each row, column, and main diagonal. All right, so how do we whittle this down? Well, we note that along the diagonal, there's only one possible solution, which is this one. So this one right around here has to be that. This has to be there. And in which case, we know, well, that the last one, theta, has to be there. And we solve for that one, which is nice. Really good. Making a lot of progress. And let's next go to Pitchfork because it's in the middle. And why do we know it's in the middle? Well, let's look at the top left, bottom right diagonal. It can't go here because of, well, this one, and it can't go here because of, well, this one. So it must be in there, and that eliminates the diagonal on both ends, so it no longer can be the diagonal, but it wasn't in that. So basically what I'm trying to say is it can't go here, can't go here. So the bottom one has to go there because it can't go here because of that one in the middle, can't go here because of that one that was original, and it can't go here because, again, along that diagonal. Right, which leaves the last one up here, which is really nice. Really, really nice and fun. Let's go on to omega. Omega completes this diagonal, which is, well, nice. Unfortunately, that doesn't do much because, again, it could be here or here. And let's just fill in all the other omega spots. Right. Or, sorry, that would not be nice, except for the fact that, oh, we have one more? Right. Now, this is how I like to tackle some of the harder ones sometimes, like on medium and hard and whatnot. So let's start from the bottom up. So we have 1 in this row, 3 in the next row, and 2 in the top row. Since there's only 1 in the bottom row, that means this has to be it. So we can eliminate this one on the same column as it, and this one in the same diagonal, and that's that. And we can eliminate the one that contradicts both of them, because again, now it's a 2-1, going from bottom up. So we can eliminate this one, and this is the only possible solution. Let's talk about sigma. Sigma has to go here. 8's the only remainder. Sigma has to go here on the bottom row because, well, this is blocked from the one we just placed, and now that bottom one blocks this spot, so sigma must go here. And last but not least, it's right there. Right, and now we're on to triangle dude. Triangle dude, we just fill in the blanks. And yeah, I love games like this. They're really fun and whatnot, but yeah. So let's take a quick 1-second break